So this problem says find the Maclaurin series of fx equaling the integral of ft dt from 0 to x by integrating the Maclaurin series of f. So what we're going to do here is we're going to take this f of x here and we're going to integrate it, but we're going to use a Maclaurin series. Now if you watched the last video, we actually showed this series for this sine of t over t. Okay, so what we're going to do here is we're actually going to integrate, but using the series instead of the function itself. All right, so here we go. So we're going to take the integral from 0 to x of not the sine of t dt, but of the sum n equals 0 to infinity of -1 to the n t to the 2n over 2n plus 1 factorial. And what we're going to do is we're going to integrate that dt. Don't forget my dt. We're going to integrate it term by term. So what does that mean for us? That means we're going to integrate from 0 to x. So we're going to just break down all of the terms here. So I wrote them all out for you. We're just going to take them all, this whole thing, all the way to infinity, and we're going to integrate it. All right, so this is going to be dt. So now we can see that this is going to be just a simple power rule that we're actually doing here for this integration. So I'm going to put equals here. So when I integrate 1, that's just going to be t. And when I integrate this t squared over 3 factorial, that's actually going to be minus t cubed over 3, and that's times the 3 factorial, and then plus, and then this is going to be t to the 5th, and then there I'm going to get a 5 here, and then, oops, let me do it this way so it'll stay the same. So then I get a 5 factorial here, and then I'm going to get a minus here, and that's going to be a t to the 7, and then that's going to be a 7 times 7 factorial, and then plus t to the 9 here, and that's going to be 9 times 9 factorial plus dot dot dot. Now remember, we're integrating this, and we have bounds for this, so this is going to be from 0 to x. And we can see how when I plug my upper bound in, I'm just plugging in x's where all the t's are at, and then minus the lower bound here. When I plug in 0 for each of these, when I plug in 0 for each of these, they're all going to zero out. So when I do that bottom bound, it's just going to be 0. So I'm actually only going to get the top bound, the upper bound here. So that's going to be x, oops, not plus, but minus x cubed over 3 times 3 factorial plus x to the 5th over 5. Let me do a better 5 than that. 5 times 5 factorial minus x to the 7th over 7 times 7 factorial plus x to the 9th over 9 times 9 factorial plus dot dot dot. Okay, now that's actually when I subbed it in. So what series is this going to give me now? That's a good question. So then this series is going to be n equals 0 to infinity, and that -1 to the n should satisfy my 0. Keep that in mind. It's going to be a positive for the first one, negative for the second. That's that pattern. So we always got to look for those. X to the 2n plus 1, because that's my odd formula pattern there. And that's going to be over, now keep in mind that these numbers here, up here, match the two numbers down here for each of these. So for each of those, that's what it's going to be. So that means this is going to be 2n plus 1 times 2n plus 1 factorial. So that's going to be the series that we're looking for this problem here. So it's very nice that we can use other ways to integrate instead of the functions themselves. Sometimes it's a little bit nicer to deal with those than it is the actual functions. So that wasn't too bad. And if I could see that from the series itself, from this one here, just looking at the series there, if I integrated, I know it's going to go up to n plus 1. And then what does that mean? I'm going to have to divide it by the 2n plus 1. And look at our answer there. It's identical to that. So if I can understand those principles of integrating, even term by term, you notice that that answer was the answer we ended up with down there when I actually integrated. So that's what's kind of cool about this, is if I do the integration, it should just match that way. So very nice.